Parametric equations didn't come up in paper 1, so it will definitely come up at least once in paper 2. And this here, in my opinion, is the hardest question they have ever asked on parametric equations, especially part C. Part C is a really difficult question. So pause the video, everyone have a go at the question, and I'll go for the answer now. Okay, so for this question, we're given this figure here, and we're told this is a sketch of the curve C with parametric equations x is equal to 2 tan t plus 1 and y is equal to 2 sec squared t plus 3. And we're given this domain here for t, where it has to be between minus pi over 4 and pi over 3. So this is the curve here, C, and we're told the line L is the normal to C at the point P where t is equal to pi over 4. So the point P is this here, and the line L is a normal to C at this point P, okay? And for part A, we need to use parametric differentiation to show that an equation for L is this here for 5 marks. So we need to find an equation for this line L here. Now, if you remember the formula for the equation of a straight line, it's y minus y1 is equal to mx minus x1. In order to use this formula here, we need two things. We need the gradient of the line, which is m, and we need a point on the line, which is x1, y1 here, okay? Let's start with the gradient for this line here, L. So this is a normal, and if you remember one of the features of a normal, so we have this curve here, C, and at this point P, let's say that the gradient of the curve is m, the normal is perpendicular to the curve. And if you remember the gradients of perpendicular lines, it's going to be the negative reciprocal of the line it's intersecting. So it's going to be minus 1 over m, like this here. This is going to be the gradient of the normal, which is L. And one thing that's useful about this, we're given a bit of a clue in part A because it tells us to use parametric differentiation. What we're going to do is, because we have these parametric equations here for C, we're going to differentiate this in order to get dy over dx, find the gradient at this point P for the curve, and then find the negative reciprocal of it, and this is going to be the gradient of the normal. Okay, so we need to differentiate these parametric equations here in order to get dy over dx. Now, I did a video on parametric differentiation. The way that you do parametric differentiation is to find dy over dx. We need to do dy over dt divided by dx over dt. Now, the way that I remember this personally, this isn't actually how it works, but if you have dy over dt divided by dx over dt, if you think about this like fractions, this is going to be dy over dt. Remember, when you divide a fraction, you flip it, so this is the same as multiplying by dt over dx, and this dt will cancel out this dt to leave us with dy over dx. This is the way that I remember it personally, even though this isn't mathematically how it works. So we have this formula here, so we need to find dy over dt and dx over dt, so we need to differentiate these parametric equations here. Let's start with y and find dy over dt. So this is going to be dy over dt. So if we differentiate this here, so if we differentiate 2 sec squared t, so it's going to be 2 multiplied by, and if we differentiate sec squared t, now we need to use the chain rule to differentiate this here. Now, there are loads of different ways that people do the chain rule. The way that I personally do the chain rule is I say that the chain rule is the inner function differentiated multiplied by the outer function differentiated. So if we look at this example here, this sec squared t, I've rewritten this as sec t to the power of 2, as this is easier to differentiate using the chain rule. I say here that the inner function is inside the bracket here, so this is this sec t, so this is the inner function, and the outer function is this power of 2 here. This is the outer function. So the chain rule is the inner function differentiated, so it's this sec t differentiated. This is one of the trig functions that you need to know how to differentiate. If you differentiate sec t, this is equal to sec t tan t, so this is sec t tan t if you differentiate the inner function, and then this is going to be multiplied by the outer function differentiated, which is this power of 2 differentiated. Think about this like x squared. When you differentiate x squared, the 2 comes down as a coefficient like this here. When we differentiate the outer function, we don't touch the inner function, we just keep this as sec t like this here, and then this power of 2 is going to go down to a power of 1 like this here. And we can simplify this because here we have 2 times 2, which is 4. We have sec t multiplied by this sec t to the power of 1, which is going to be sec squared t, like this here. And then we also have this tan t here. We also have this plus 3, but as this is a constant, when you differentiate a constant, it just goes away. So this is dy over dt here. So now we need to differentiate this x parametric equation here in order to get dx over dt. So this is going to be dx over dt is equal to, so if we differentiate this here, it's going to be 2 tan t, so it's going to be 2 multiplied by, and if you differentiate tan t, again, this is one of the trig functions you need to know how to differentiate. This is equal to sec squared t, like this here. We have this constant plus 1, which when we differentiate it, it just goes away. So this is going to be equal to 2 sec squared t, like this here. So this is dx over dt. So dy over dx is equal to dy over dt divided by dx over dt. So dy over dx is equal to dy over dt, which is this 4 sec squared t tan t, and this is divided by dx over dt, which is this 2 sec squared t, like this here. We can simplify this, so we have 4 divided by 2 here, so this 2 will cancel out and leave us with a 2 in the numerator here. This sec squared t will cancel out with this sec squared t, so we're just going to be left with 2 tan t here. So this here is dy over dx. Now we need to find the gradient of the curve at this point P, and we are told that this point P is where t is equal to pi over 4. So we can sub in t is equal to pi over 4 here. So we can say that dy over dx is equal to 2 tan of pi over 4. Tan of pi over 4 is equal to 1, so this is going to be 2. So this here is the gradient of the curve at this point P. We need to find the gradient of the normal, which is going to be the negative reciprocal of this here. So therefore the gradient of the line, the normal, is going to be the negative reciprocal of 2, which is minus a half. Okay, so we found the gradient of the line, so now we need to find the coordinates of a point on the line, and we know that the point P lies on this line L here, and we know that the point P is where t is equal to pi over 4, so therefore we can figure out the x and y coordinates of this point P by just subbing this t is equal to pi over 4 into these parametric equations here. So if we do this, so it's going to be x is equal to, so it's going to be 2 tan t, but instead of t it's going to be pi over 4, and then it's plus 1, and if you put this into your calculator, this is equal to 3. So x is equal to 3 at the point P, and y is equal to 2 sec squared of t, so this is going to be pi over 4, and then plus 3, and if you put this into your calculator, this is equal to 7. So therefore the point P is equal to 3, 7, and this is a point on the line L here. So therefore we have the gradient of the line L and we have a coordinate on the line. So therefore we can sub this into the equation of a straight line. So we can say that it's going to be y minus y1, so it's going to be y minus, and then y1 here is 7, is equal to m, and we know the gradient of this line here is minus a half, and then x minus x1, so this is going to be x, and then it's going to be minus 3, like this here. We need to write it in this format here where y is the subject. So if we do this, so it's going to be y minus 7 is equal to, if we expand this bracket here, it's going to be minus half x, and then it's going to be plus 3 over 2, and then move this minus 7 to the other side, so we get that y is equal to minus a half x, and then move this minus 7 to the other side, so it's going to be 7 plus 3 over 2, which is equal to 17 over 2, and this here is the final answer that we need. Okay, and then for part B, we need to show that all the points on C satisfy this equation here for 2 marks. So this is just your bog standard parametric equations question, where you need to convert this parametric equation here into this Cartesian equation here. Now, a bit of a clue, there is a couple of ways that you can do this question that's mentioned on the mark scheme. A bit of a clue for how to approach it is here we have a tan and here we have a sec squared, and this is a clue that we need to use the identity that 1 plus tan squared x, or in this case t, is equivalent to sec squared t, like this here. If we rearrange to make tan t and sec squared t the subject, we can therefore sub them into this identity here and get an equation that only involves x and y. Okay, so if we do this, so we have these parametric equations here, that x is equal to 2 tan t plus 1 and y is equal to 2 sec squared t plus 3. Let's start with the x parametric equation. Let's rearrange in order to make tan t the subject. So let's move this plus 1 to the other side, so it becomes x minus 1 is equal to 2 tan t. Then divide both sides by 2, so we get that x minus 1 over 2 is equal to tan t. If we then work with the y parametric equation and rearrange in order to make sec squared t the subjects, move this plus 3 to the other side, so we get that y minus 3 is equal to 2 sec squared t, and then divide both sides by 2, so we get that y minus 3 over 2 is equal to sec squared t. So we're going to use the identity that 1 plus tan squared t is equivalent to sec squared t. Now be careful, because here we have a sec squared t and here we only have tan t, so we need to square everything in this equation here. So this is going to be x minus 1 over 2 squared is equal to tan squared t, like this here. So we're going to sub in sec squared t and tan squared t into this identity here. So if we do this, it's going to be 1 plus, and then instead of tan squared t, it's going to be this x minus 1 over 2 squared, and this is equal to sec squared t, and we're going to sub in this y minus 3 over 2, like this here. Okay, let's square this bracket here. Now if you look at the final answer, we want this x minus 1 squared in the final answer, so let's not expand the brackets of this x minus 1 up here. Let's keep this as 1 plus and then x minus 1 squared, like this here, and then 2 squared is 4, like this here, and this is equal to y minus 3 over 2. Now here we have this 4 denominator, so let's multiply everything in this equation here through by 4. So if we do this, it's going to be 1 times 4, which is equal to 4. Then this denominator is going to cancel out and leave us with x minus 1 squared, and this is equal to, so 4 times this here, this 2 denominator is going to cancel out, leave us with times 2 of this y minus 3, which is going to be equal to 2y minus 6. We need to make y the subject, so move this minus 6 to the other side, so we get that 10 plus x minus 1 squared is equal to 2y, and then divide both sides by 2, so we get that y is equal to a half x minus 1 squared plus 5, and this here is the final answer that's required. Okay, so for part C, we're told the straight line with equation y is equal to minus a half x plus k, where k is a constant, intersects C at 2 distinct points, and we need to find the range of possible values for k for 5 marks. So I'll be honest, the reason that I've titled this video the way that I have is because of this question here, part C. I think this is really difficult, especially to get all 5 marks. So if we look at this diagram here, so the line is y is equal to minus a half x plus k, so it's going to have a gradient of minus a half, and it's going to have a y-intercept of k, and it's going to intersect C at 2 distinct points. So it's going to look something like this here. So this is going to have a gradient of minus half, and it's going to have a y-intercept of k, and it intersects C at 2 distinct points here and here. So hopefully you can appreciate that there are multiple lines that can intersect C at 2 distinct points. It could be above this line, for example, where it intersects at 2 distinct points, or it could be below this line as well, where it intersects C at 2 points. So that means there are a range of values for k, the y-intercept. So how do we find these range of values for k? Remember, in part B, we found that C is a quadratic. It's y is equal to half x minus 1 squared plus 5. You might need to do some revision on this. This is going way back to year 1 of chapter 3. We talked about points of intersection between a straight line and a quadratic. It can either have 2 points of intersection, 1 point of intersection, or no points of intersection. If it has 2 points of intersection, what we can do is we can equal these two equations to each other. So we can say that minus a half x plus k is equal to a half x minus 1 squared plus 5. If there are 2 points of intersection, this means the discriminant b squared minus 4ac is bigger than 0. Remember this, if there was 1 point of intersection, it would be equal to 0. If there were no points of intersection, it would be less than 0. But here, the discriminant b squared minus 4ac is going to be bigger than 0, and we can rearrange this in order to get it into the quadratic equation format, and then sub these values into the discriminant and find an inequality for k. Okay, so let's get this into the quadratic equation format so we can use the discriminant. Now we have these 2's in the denominator here, so the first thing to do, just to simplify this, let's multiply everything through by 2. So this minus a half x will become minus x, and now this will be 2k like this here, and this will be equal to, and then this half will go away and just leave us with x minus 1 squared like this here, and then 5 times 2 is 10 like this here. So we can simplify this. We have minus x plus 2k. If we expand this x minus 1 squared, it's going to be x squared minus 2x plus 1. Then we have the plus 10 on the end, and then we can write this as minus x plus 2k is equal to x squared minus 2x, and then 1 plus 10 is equal to 11. And then if we move this minus x plus 2k onto the other side of the equation, so this here is still going to be x squared. We have this minus 2x, and if we move this to the other side, it's going to be plus x, so this is going to be minus x like this here. And then if we move this 2k to the other side, it's going to be plus 11 and then minus 2k like this here, and this is equal to 0. So the discriminant b squared minus 4ac is bigger than 0. So here a is going to be 1 because the coefficient of x squared here is 1. B is going to be minus 1 again because the coefficient of x here is minus 1, and C is going to be this 11 minus 2k. You can put this in brackets like this if you like. So therefore, if we sub these values in, it's going to be b squared, so it's going to be minus 1 squared minus 4, and then a is 1, and then C, which is 11 minus 2k, and this is bigger than 0. Let's rearrange this in order to make k the subject. So minus 1 squared is 1. Then we have minus 4 times 1, so this will just cancel out. So minus 4 times 11 is going to be minus 44, and minus 4 times minus 2k is going to be plus 8k like this here, and this is bigger than 0. And then 1 minus 44 is minus 43. Then plus 8k is bigger than 0. Move this minus 43 to the other side, so we get that 8k is bigger than 43, and divide both sides by 8, so we get that k is bigger than 43 over 8. So this here, we have this inequality where k has to be bigger than 43 over 8. Okay, so this is where this question gets quite difficult in my opinion. So if this question was just that you have two lines, y is equal to minus a half x plus k and y is equal to a half x minus 1 squared plus 5, and you need to find the range of values of k for which there are 2 points of intersection, this here would be the final answer and you would get all of the marks. However, for this question, if you gave this as your final answer, you would only get 2 of the 5 marks. The reason for this is, remember that this line here, y is equal to a half x minus 1 squared plus 5, is defined by these parametric equations here, and importantly by this domain here where t is between minus pi over 4 and pi over 3. If you look at this graph here, it looks quite weird because you can see the y-axis goes all the way to here, but the line C doesn't go all this way. If this was a true quadratic, this line would keep going up like this here and keep going up like this here, but it doesn't because we have this domain here where t has to be between minus pi over 4 and pi over 3. X is equal to 2 tan t plus 1. If we sub in the lower limit of minus pi over 4 and the upper limit of pi over 3 into this here, so if we sub in the lower limit, it's going to be x is equal to 2 tan t, so instead of t it's minus pi over 4 and then plus 1. If you put this into a calculator, just figure it out, it's equal to minus 1. If you sub in the upper limit, so x is equal to 2 tan of t, so the upper limit is where t is equal to pi over 3 here, and then plus 1. If you put this into your calculator, if you round it to decimal places, it's equal to 4.46. So this is the minimum value that x can have, and this is the maximum value that x can have. And what this means is we don't get these sections here. X only goes up to here, so this is where it's equal to minus 1, and x only goes up to here, and this is where it's equal to 4.46. Okay, so hopefully that makes sense, but you might be thinking to yourself now, why does this matter for the final answer? The reason because is, let's say that we had this line here. Now, when you first look at this line, you might be thinking that it has 2 points of intersection with the curve. It has 1 point here and 1 point here. However, it doesn't. It only has 1 point of intersection. And the reason for this is because, remember, because of the t domain, this section of the graph doesn't actually exist for C. So therefore, this point of intersection over here, this isn't a point of intersection. This point here is, but this point isn't. So there is actually only 1 point of intersection for this line, and therefore this here is not the final answer. This means there is actually an upper limit for what k can be as well, and we'll call this a. There is a maximum value that k can have in which there are 2 points of intersection. Otherwise you get this effect here, where on this side this is not a point of intersection. Okay, so how do we find this value of a? How do we find this maximum value of k? Well, the highest that the line can be, and therefore the maximum value that k can have, is when it intersects with the highest point on this side of the curve. So this is going to be this point here. So therefore the line is going to look something like this here, where it also intersects with this point here. If it's anything higher than this, so for example this line here, we're going to get the effect we talked about before, where it intersects on this side but it doesn't intersect on this side. So therefore this is the highest that the line can be, and this is going to be the maximum value of k. So how do we find this? Well, we know that this point here is going to exist where x is equal to minus 1, because we know that this is the lower limit of x. So what we can do now is we can just sub this into this equation for c in order to find y. So we can say that y is equal to half, and then instead of x it's going to be minus 1, so it's minus 1 and then minus 1 squared and then plus 5. So therefore y is equal, if you put this into your calculator, to 7. So y is equal to 7 here. So this point here is minus 1, 7, and the line intersects with this point. So therefore what we can do is we can sub these x and y values here into this equation of the line here in order to find k. So it's going to be y, which is 7, is equal to minus half and then x, which is minus 1, and then plus k. So this is going to be 7 is equal to, and then minus a half times minus 1 is going to be a half, and then plus k, and then move this half to the other side, so it's going to be 13 over 2 is equal to k. This here is the maximum value that k can have. Anything higher than this and we get the effect we talked about before, where it doesn't intersect on this side. So therefore this is the maximum value of k, so this is the value of a. So therefore k has to be bigger than 43 over 8, but it has to be less than 13 over 2. And to make matters even more complicated, it can also be equal to 13 over 2 as well, because t can be equal to minus pi over 4. And this here is the final answer, and you get all 5 marks for this here. As I said, I think this is a really hard question. Really, really well done if you had a go at this yourself and you got all 5 marks. When I was doing my A levels, I don't think I would have got all 5 marks for this question. Just really quick, something I'm adding on here. When I was editing this video, there was actually a part of me thinking of not uploading it, simply because of how hard part C is, especially how close it is to paper 2 now. I didn't want people kind of losing confidence coming up against a question they didn't know how to do. I really need to emphasize how hard part C is. This is actually the examiner's report from that year in this paper, and they also talk about the fact how few people got all of the marks for that question and how few people got part C right. Firstly, this was also the last question in the exam, so a lot of people didn't have time to do it anyway, but they talk about the 4 part C. There was such a small number of people that were able to get all of the marks for it. Really don't panic if you weren't able to get the answer. It's a really difficult question. As I said, if I was sitting this when I was doing my A levels, I don't think I would have been able to get all 5 marks.